Ladies and gentlemen, welcome to the last talk.
Yeah!
And let's give Kale a round of applause for running here with the last bit of whiskey. Because this is Max's first talk at Defcon, and it takes a lot of work. So.
Go back!
All right, so raise a glass if you got it.
Cheers, guys. Nice.
All right, enjoy the last talk.
So, hi everyone. My name is Maksim Shudrak. Friends call me Max. I am a researcher. This is the last Defcon talk this year, which is really sad, but we're going to talk about malware fighting in the next 45 minutes, which is cool. So, let's go. First of all, I'd like to thank Defcon goons who gave me a chance to speak on this stage. This is a real honor for me, and this is the first Defcon in my life ever. So I'm talking, and this is the first Defcon. I'm really excited and enjoy to be here. Originally, I'm from Russia. Defended PhD there in null research in 2016. Had a chance to work on malware analysis in Israel for 2 years. And since 2018, I've been living in the Bay Area, so I'm with you guys. As you can see, my background combines experience in malware analysis and fuzzing. So one day I got an idea, why not try to search for bugs in malware? Sounds like a crazy idea, but my good friend Jonathan Rossers, who actually inspired me to present this talk, was excited. So this presentation is logically divided into 3 parts. In the first part, I'm going to explain why, where, and how we can search for bugs in malware. Why coverage-guided fuzzing is the best technique to search for these bugs. What kind of problems we have to address to be able to find bugs in malware. And of course, I'm planning to show a demo of my fuzzer implemented on top of WinFA. In the last part, I'll show you several cool zero-day I found in different malicious samples and explain future directions of work. So before I actually start fuzzing binaries, I decided to find and look over some leaked malware source code files, and just to understand that this idea makes sense and it's worth to spend time on it. And guess what? Right in one of the first source code files, I found this comment in Russian, which can be translated in the following way. So I was really laughing for a couple of minutes. I thought, okay, looks like this idea makes sense, and I'm gonna find some bugs in this sample and probably in another. By the way, it's carbon. So when they write malware, they have to do a lot of complex things like initial infection, payload delivery, and most importantly for us, communication with C&C server. There are a lot of things that can potentially go wrong here. So an ideal place for us to search for bugs would be some complex parser of incoming commands from C&C or some complex file format parser. While some samples leverage very trivial algorithms to communicate with C&C, there are a lot of samples that support really complex communication protocols implemented from scratch. Despite of this complexity, bad guys usually are rarely interested in implementing secure code for many reasons, such as lack of time, expertise. So in most cases, we will not see things like SLR, DEP, or any other anti-exploitation techniques, which is actually good for us. Sometimes the code is so badly written that malware doesn't work if the environment has slightly changed. This tweet actually explains it a lot. So, and of course, searching for bugs in bad guys' code could not be boring. So, I hope you think the same. So, hacking back in general is pretty well-known research topic. There were a bunch of great talks at Defcon presented in the past. I can safely guess this idea has lived with hackers community for decades. I just listed 2 of cool Defcon talks presented last year. But what about fuzzing malware? Well, there are much less publications in this field. Actually, there is no systematic research on this topic at all. I found several research papers published by academia, but The main goal of this research was to find and trigger some malicious code paths hidden in malware using fuzzing, which is a bit opposite. In this talk, I'm focusing on bugs hunting and how we can use these bugs to defend against malware. So, legal issues. It's less relevant for this talk, but anyway, I want to say that hacking back is in very deep gray zone. There are a lot of questions with attack attributions, scopes of attack, and a lot of other things. So, but no one can stop us to search for bugs in malware, so it's obvious. Cool, we now understand our motivation and legal aspects. Let's say we found some bug in malware. What kind of benefits we can get from that? Let's imagine that we found some memory corruption bug that led to crash in some sample that are spreading around the planet. Such bug actually might be quite useful. I guess many of you remember a famous kill switch found in WannaCry, which significantly helped to slow down spreading of this sample. If you place one file with special name in one specific folder, WannaCry will not infect your machine. Of course, they left this kill switch on purpose. But if we can automatically or semi-automatically find some memory corruption, for example in some complex file parser, we don't even need such gifts from them. We can just place this file in our operating system and malware will not infect this machine. Besides that, if we can somehow trigger such bug remotely, we would be able to do a lot of other cool things. We can stop malware from spreading over our network, or slow down it, or shut down existing agents just by modifying network packets coming to and from C&C. It's especially cool if we can do that against botnets that are trying to perform a DDoS attack against us. For example, if bots have some vulnerability in the victim's response parser, we just need to send our exploit back to bots, and it will cause a crash. Later in the demo, I'll show that actually it's possible. Well, it would be really great if you can trigger remote code execution here. Of course, we can take control over botnet, or shut down existing agents, or track down botnet owners, and do a lot of other cool things here. And of course, our sweet dream bug is remote code execution on C&C. In this case, we have God mode and can do everything. But in my opinion, it's less likely today because most C&C are written in memory-safe languages like Python, PHP, Go, or any other. I don't see any reason to write it in C or C++. Okay, how can we search for these bugs? Today, fuzzing is the most efficient technique to search for bugs in memory-unsafe languages. Actually, fuzzing is very important for software security at all. Top tech companies, huge open source projects who integrated fuzzing within development lifecycle, they all report that this technique improves security of their products. Linus Torvalds recently said that fuzzing actually improves security of Linux kernel, which is really cool. Okay, what's fuzzing? Fuzzing is actually a very simple technique. You provide potentially invalid or malformed input to your program and monitor your program for crash. Nothing hard. So you start with fuzzer generates input and sends this input into your program. All you need is to sit and pray that it will find some cool crash for you. This picture actually precisely explains my feelings when my fuzzer reports a new unique crash. I usually very happy, like really happy. Okay, what is coverage-guided fuzzing? Many years ago, when fuzzing was dumb and blind, fuzzers considered the program as a black box, into which we send our test cases. It usually worked pretty good for trivial bugs that located not deep in the code. People wanted to find more complex bugs deeper in the code, so they decided to instrument program under test at compilation stand and provide this coverage back into our fuzzer to be able to improve test case generation. So the best example of such fuzzer is American Fuzzy Log or AFA. So during coverage-guided fuzzing, if we manage to find a test case that triggers a new code path in our program, the fuzzer saves this test case and then performs subsequent mutation on top of this new file. The same for the next code path and for the next, and this way we can touch much more code deeper in the program and find more bugs. In theory, of course, dumb blind fuzzer at some point can also find this path, but it can take a lot of time to find them. So the best example is this code. In case of coverage guided fuzzer, it's going to take about several minutes to find this null pointer dereference. But in case of dumb blind fuzzer, it can take years to find the same problem. So you see why coverage guided fuzzer is a really powerful tool. It can be so effective. Okay, today there are two state-of-the-art fuzzers. It's AFL and UFuzzer. There are a lot of AFL forks implemented on top of AFL. So, for example, I really recommend this kernel fuzzer KFL. And what is more important for us, there is WinAFL, a port of AFL for Windows binaries. Sorry. So, AFL injects instrumentation routines during the compilation step. So, the resulting binary will have this AFL main belong function injected in each basic block. In case of malware, we have one tiny problem. We don't have source code, so I guess it's not a surprise, right? Actually, we have even more problems. Malware usually unpack and execute code, most important part of malware, dynamically at runtime. In this case, source code instrumentation is useless. We have to find some way to be able to provide back to our fuzzer coverage of such dynamically unpacked and executed code paths. And we can try some other tools and techniques of automatic malware deobfuscation. But in my opinion, it's less scalable and works only for a specific subset of samples. So, besides that, if you want to search for bugs in C&C communication, we have to encrypt our test cases the same way as malware. So we have a lot of problems here. But thanks God, WinAFL doesn't need source code for binary fuzzing, so we don't need source code of our sample. Instrumentation is implemented on top of DynamoRio, Dynamic Binary Instrumentation Framework. What is dynamic binary instrumentation? I'll call it DBI. DBI is a technique of analyzing the behavior of a binary application at runtime through the injection of instrumentation code. I just want you to give a basic idea how it works. Let's say we have our DBI engine and binary we want to instrument. At step 1, DynamoRio launched this binary suspended, inject instrumentation library, hook entry point to redirect control flow into instrumentation library, and resume execution. So at this point, it looks like a traditional classic DLL injection and control flow hijacking. But at step 4 starts the magic. DynamoRio takes the first basic block, copies it, and in a special place called code cache, then it performs transformation of this basic block to be able to inject instrumentation routines, instructions specified by a user, and then execute it in this special code cache. The most challenging stuff is to make this execution transparent towards instrumented binary, and DynamoRio knows how to do that. It's really complicated task, and they're doing pretty good. So then we take next basic block, copy it in code cache, perform transformation, inject our instrumentation routines, execute it, take the next one, and so on until we reach exit point of our program. So you can see, this way we can instrument everything that are executed on our CPU. So we had 3 challenges: lack of source code, obfuscation, and encryption. WinAFL plus DynamoRio solves the first problem and actually creates a new one. WinAFL supports only file-based fuzzing, so we can't actually perform fuzzing of network traffic parsers, which is a very serious limitation for us. To address this problem, I decided to implement a patch on top of WinAFL and call it NetAFL. Suppose we have our fuzzer and our malware instrumented by DynamoRio in memory. Let's assume our sample sent some request to C&C. Instead of actually send it to C&C, we redirect this request to our fuzzer. Our fuzzer generates a new test case, encrypt this test case if it's necessary, and then send this response back into our sample. Then we update our coverage bitmap triggered by this test case, estimate code coverage, provide this code coverage back to our Fuzzer, and Fuzzer generate a new test case, restart our sample or target function in our sample, and repeat all previous steps. It sounds like a bit complex scheme, but it's actually pretty easy to use. All you need is to specify IP address, port to listen on, and seed file. That's it. The Fuzzer will do all the rest for you. If you need to encrypt your test case before send them back into our sample, you can provide a path to your custom encryption library. NetFL will load this library and will use this explicit function to encrypt test cases. If you don't like default C&C, you can define your own one. If, for example, you need to implement some really complex communication logic with your target. Okay, let's see how it actually works. Okay, here we go. So in this virtual machine, I have a release build of NetFL. But before actually start our Fuzzer, let me explain the code we are trying to analyze. So it's Dexter version 2, malware designed to steal point of sales, designed to steal credit and debit card information from point of sales terminals. So in this function, HTTP main, they have initialization, so they generate agent string, then they open connection with C&C using standard Windows API functions. So they will use post request to send commands to C&C. Then it gathers some information about victim's machine and then actually send this data via standard Windows API functions. If they successfully send this data, they call this function getCookie. So let's go in this function. In this function, they receive commands from C&C coming back via browser cookies. So this function, internet get cookie, is used for this purpose. So it's very trivial function. You just call it and you get your command, and you get your cookies in p command variable. So then they perform some fuzzing. They perform parsing of this command, and then let's go back. If they manage to obtain it, the end command starts with $. They are going to execute this command. So this way they implement communication with C&C. So as you can see, we need to implement some non-trivial communication logic with our C&C. So we need to implement our custom C&C library. Okay, it's actually not hard. All we need is to define two functions. So this is our custom C&C. We need to define C&C need that receives server port to listen on. Then we have like standard initialization of these sockets. And then we can call listen on this port. And we have to implement the second function, C&C run. It receives test case from NetFL for each generated test case that NetFL wants to send in our sample. So in this case, we have to accept this connection, receive this data coming from our malware, generate our response. We have to say for our malware that everything is okay, we receive your request, this is your response, and you can get your cookies. Then we generate cookie. There is a nice function from Microsoft Internet Set Cookie. We generate this cookie on top of data provided by NetFL, and that's it. So this way we can compile this binary and provide path to our Fuzzer. Okay, this is command to run NetFL. It looks like a pretty long command, but actually it's not hard to understand. The first argument defines a path to our custom C&C library. The second parameter is port to listen on. The third and second and fourth parameters standard AFL in and out directories. In directory we should have seed file. -d specify address of our Dynamo binaries. -t is timeout. Then we have internal WinAFL arguments. You can find detailed explanation on GitHub. And then we have really important argument fuzz iterations. This argument tells netFL how many iterations should pass before actually restart the whole target sample. So this parameter can directly affect your stability. So this is very important. So in my case, I choose 5,000. It works pretty well for me. So, and the last parameter is the path to our malware. Okay, let's run. So it's initialization, everything loaded successfully, initialized. In a few seconds we will see standard AFL screen. Okay, here it is. It's not related. So as you can see, our Pfizer stats looks pretty healthy. We already found like 6 paths. We have coverage. Our stability looks pretty good, 97%. Execution speed is growing, but it's still very slow because we are running a very slow virtual machine with no parallelization. But if you can leave our Pfizer like this for a couple of hours, we can find bugs. Okay. Let's start. So if you leave our Pfizer for 4 hours with no parallelization, it will easily find several bugs in our sample. Okay, great. Let's see what I managed to find in malware. First malware I selected for my experiment was Mirai. Mirai is malware that targets IoT devices and uses devices as a part of botnet for large-scale DDoS attacks. This malware was used in some of the largest and most disruptive DDoS attacks in history, which caused major internet platforms and services to be unavailable for large amount of users in different regions of the world. In 2017, source code of Mirai was leaked, and different Mirai-like botnets adapted this code and still operating in the wild. The fun fact about Mirai is that it looks like authors even followed some security practices and use memory and debugging tool electric fans to search for heap overflows and use after pre-bugs, which is a bit unusual for malware. Mirai DDoS capabilities are based on HTTP flood and several low-level network attacks. The most interesting part for us in terms of exploitation would be this HTTP response parser. Mirai needs to parse HTTP response coming back from victims to be able to perform HTTP flood attack. This parser has about 830 lines of code, hundreds of potentially dangerous operations with memory, with pointers, strings, so this is a wonderful target for our Pfizer. As a seed file, I decided to use this very basic HTTP response. I ran my Pfizer for 24 hours and managed to find 43 unique crashes, which was caused by a single bug in relative URLs handler. Execution speed was around 1,000 executions per second, which is pretty good. And Pfizer managed to find approximately 430 unique paths, which is also pretty good. What was the root of this bug? If our HTTP response contains a relative URL, this const branch is triggered. In case of incorrect relative URL, variable "i" always equal negative values, which cause a memory violation and crash. This is logical error. So authors forgot to set up this argument to 0. They use it in code early and forgot to set it in case of relative URLs. So this is one example of test case that was a crash. So if you see that Mirai or Mirai-like botnet is trying to attack you, you can just answer these bots with this HTTP response and they will all crash. So let me show how it actually works. So in this virtual machine, in the right terminal, we have our, just a second. In the right terminal, we have our HTTP server, our victim, implemented in Python. So it's just a simple HTTP server. In the left part, we have debug build of Mirai. Debug build because we want to see what's actually going on. And in debug build, they're printing a lot of information, which is useful for demo. Okay, let's start our server. So I guess it's start and running. Before actually start Mirai, let me explain one thing. So before actually start HTTP flood attack, they need to connect with C&C. I was too lazy to deploy actual C&C server, so I decided to implement in this Python script C&C and just response like random data to our Mirai sample. And surprisingly for me it worked. So after dozens of attempts, it actually started HTTP flood, which was good. So it was like really easy solution for me. So to be clear, my Python server are now doing two jobs. The first one is to be a HTTP response server victim, and the second one is to be a C&C for our Mirai to answer that everything is okay, I'm up, let's start. So okay, let's run. So you can see it starts in debug mode. It tries to attempt to connect with C&C, and after dozens of attempts, it will receive some meaningful data and actually start HTTP flood. Okay, here it is. So it's starting HTTP flood. It's sending HTTP request to our Python server, and Python server is going to answer with this malicious HTTP response I showed in the previous slide. Okay, so here it is. We have segmentation call and crash. So profit. This way we can stop Mirai attackers. Okay, thank you. There is more bugs in different samples. So I already presented this sample when I was showing NetAFL. This is Dexter version 2. The first version of Dexter was one of the first known botnets that targeted point-of-sale terminals. As I already said in the demo, Dexter communicates with C&C or HTTP protocol via POST request and receive commands over the response cookies. Actually, in case of Dexter, you don't need fuzzing at all. The malware code is so badly written that you can just answer with a long command and it will crash. And actually it's remote code execution. You can find actually, do you see this URL? It has 255 bytes. We can send a command longer than this 255 bytes, and it will cause Stack Overflow, and we can exploit. And as I said before, there is no anti-exploitation techniques. It's like 90s. We can easily cause remote code execution. So really old school bug. Tiny Nuke. Tiny Nuke is a Zio-style banking Trojan designed to perform man-in-the-browser attack using web injects. It has a function load web injects. The name of this function, I guess, is pretty self-explanatory. It is designed to ask C&C server provide a payload to be injected in the victim's browser, and then this response it's represented as JSON in JSON format. It's then passed into our custom JSON parser. This JSON parser actually is very, very complex. They implemented from scratch, so it's very good target for us. This is example of seed file I used to feed in NetAFL, and after 24 hours of fuzzing, I had pretty good results. 3 unique paths, 800 executions per second, and 4 unique crashes. The root of these crashes is this function. It causes infinite recursion in case of very long response, which contains only opening brackets. So in my case, it was like 7,000. So it will cause a very, very deep recursion, Stack Overflow, and it finally will trigger the crash in our target. So last example, Kins. Kins is a banking Trojan fully based on leaked Zeus source code with some minor technical improvements. So all bugs I found in Kins also related to Zeus. This example has been used to attack financial institution in Europe. It has HTTP response parser, so I decided to use a simple HTTP response as a seed again. The Trojan receives payload and commands from C&C or HTTP protocol. The HTTP response is then parsed by two complex routine: analyze HTTP response and analyze HTTP response body. And again, it's very interesting target for us. 24 hours of fuzzing get me 22 unique crashes, which was triggered by one problem. This time it was a bit more complex. So function getMimeHeader is used to extract a value of content length from HTTP response. But if the string contains a value, if the string doesn't contain a value of content length at all, it causes an integer overflow, and as a result, the function will return negative values. So this getMimeHeader will return negative values. But then copy X is called with this value returned by getMimeHeader. So in my case, it was always -3. It will try to override the whole memory layout of our sample. So if we try to copy with -3, it means that we are trying to override the whole memory layout. It's probably exploitable. We can sometimes control this negative value, but I'm not sure 100%. So this is example of crash case. We just need to send content length with blank value. Okay, let's discuss challenges and issues. First of all, of course, in my case, I want to say that I picked the hardest part, reverse engineering and searching for target function. I took source code to reduce time of searching for a target. Of course, for real-world samples, you need to perform like initial reverse engineering of your sample and find this target function you want to analyze. Sometimes it can take a lot of time. Secondly, of course, there are bugs in WinFL, NetFL, DynamoReal, especially when you deal with highly obfuscated samples. Third, you need to find test case, so you need a seed file. Sometimes it might be really difficult, especially if C&C is down or you don't know what kind of file malware wants, so it might be challenging. Then we have a problem with encryption. So sometimes encryption algorithm is very complex, and I know it might be really painful to perform reverse engineering of this algorithm. In this case, you can try to patch program just to disable encryption at all. It worked for me sometimes. And stability. Stability plays like critical role when you're doing coverage guided fuzzing. So if your coverage is always different when you send the same test case in your target, it means that your target is unstable and your fuzzer doesn't understand what's going on actually. So it's sending one file and it goes different code paths. It's strange, and usually it means that you waste your coverage guided fuzzer to nothing. So you have to pay attention for this. I also found this tool very useful when you want to find the target routine in your sample. I have implemented this tool on top of DynamoReal. It's basically a trace for Windows, but transparent towards instrumented program. So it will trace all API calls in malware and print this information in the file. So it's less detectable than standard API call tracer. So I hope, guys, it will work for you. You can try it. It's open source, BSD license. So, take it. In future, I guess it would be really cool if we can somehow find this target function for our fuzzing automatically. Also, it would be great to increase stability. I implemented some heuristics to make it more stable. It worked for me. I hope it will work for you. And it would be great to have some code coverage visualization tool for your fuzzer. I know there are some of them, but it would be great to adapt it for NetFL. And of course, improve stability. Okay, so I hope I convinced you that bugs in malware might be useful, and you can really find these bugs using fuzzing technique. Of course, NetFL can and should be used to find bugs in network-based application. So it's general purpose part of Fuzzer. I designed it to be general purpose. You can use it to find bugs in benign software. So I recently found one CVE in network-based application for Windows, so you can try it. And I'm also currently merging this project with WinFL, just to reduce the amount of different projects on this plane. So I guess I'm going to finish this work in 2 or 3 weeks. So you don't need, in future you will not need NetFL, everything will be merged with original branch, WinFL. And soon, probably in September, I'm going to release NetFL for Linux. I hope in September. Thank you for your attention.
Hey, it's me, Cameron Salmon. Please like and subscribe if you enjoyed this video or learned something. Comment below if you want me to continue making these types of videos.